Hello world! Thanks for watching. In this talk, we will cover a very exciting topic, neuroscience-inspired AI, an AI system that works like the brain. This could be the next biggest thing in AI. Then I'll demonstrate our approach with an object identification system. People have doubt whether we have enough understanding about the brain to build a general intelligence right now. My point is that there have already been plenty of scientific discoveries pointing us to the right direction. We cannot wait till every knowledge about the brain is handed to us. What we have to do is to piece together those discoveries systematically. With our demo, I hope you will discover that general intelligence is not in the distant future, but can be realized step by step following the guidance of neuroscience. Deep learning has achieved outstanding success. Why do we need another AI? There is one thing they are not: intelligence. As stated by Gary Marcus, it's essentially a statistical technique for classifying patterns based on sample data. He listed 10 limitations of deep learning. I'll just focus on 2 of those. First, it's data hungry. Deep learning needs lots of data to classify objects. In fact, over 50% of work is spent on data in a typical project. Even with a pre-trained model, you still need tens of thousands of pictures to get decent results. In real world, this is very troublesome. If a life has to repeat a task millions of times before learning anything, it would have already gone extinct. Second, it's a black box. Deep learning has millions or billions of parameters. Its overly complex structure and parameters make it impossible to understand its behavior. In critical applications such as auto-driving or medical image analysis, we need to understand its decision process. Deep learning is susceptible to adversary attack. Put a sticker on the stop sign, the system will mistake it for a speed limit sign. Images with abstract patterns were seen as familiar objects but invisible to human eyes. If we don't know what's going on inside the black box, fixing one problem will probably create more problems. Deep learning doesn't have a solid theory. We all know that without a solid foundation, you may build a nice house, but not a skyscraper. Counting on it to realize general intelligence is akin to building skyscraper without a solid foundation. With all this being said, we are not completely against deep learning. Obviously, it has done something right to achieve outstanding performance. Something resembles the inner working of the brain. There is something about the deep learning that we can learn from. Only after examining it carefully from the perspective of neuroscience can we find out what it has done right and what it has done wrong. The ultimate goal of AI is to achieve general intelligence. With current mainstream approach, there seems no end in sight. Innovation often comes from the outside. It's time to give outsiders a chance. The brain is a marvelous wonder, the only known structure capable of demonstrating intelligence. This is why we should focus on neuroscience-inspired AI. Deep learning is now. Neuroscience-inspired AI is the future. People use the phrase neuroscience-inspired AI in different contexts. To avoid confusion, we need to clarify what is neuroscience-inspired AI. It's about applying our understanding of how the brain works in designing an AI system. We only need to be concerned about the mechanism of information processing, not any particular form of neural network. The brain is complicated enough. Focusing on its physical form will only make things even more complicated. Before the Wright brothers, people tried to invent the flying machine by imitating birds anatomically. But the Wright brothers succeeded by focusing on what matters, the principle of aerodynamics. What it's not? It's not about neural network, not layers upon layers of complex network. Neural network is just the physical forms on the outside. It's a means to achieve the goal. The goals are extracting specific information at every stage of the visual pathway and get structured information from natural input. There is no need to focusing on the means while ignore the goals. Second, it's not about playing game, doing statistics. Although playing game, doing statistics are cool, but they are not intelligence from neuroscience perspective. AI is a mostly misunderstood and misused word. What is general intelligence? That would be another topic for our future talk. Certainly, it is also not academic computational neuroscience. They tend to focus very narrowly on a very specific problem, while we focusing on the system-level integration of diverse neuroscience discoveries. Going from neuroscience to AI is no easy task. How do we approach this problem in a practical manner? We build an object identification system on principles of neuroscience and traditional computer vision. Neuroscience provides guidance in the design of overall system and making improvement on traditional algorithm. There are many times we find that the design of some computer vision algorithm awkward, even puzzling. However, once they were redesigned following the principle of neuroscience, they became more efficient and natural. For the traditional computer vision, some algorithms perform well on certain tasks because they have already employed a mechanism resembling the working of the brain. Another practical reason that we build our system on computer vision is that since some of them have already performed better on certain tasks, integrating them would only make our system perform better. So we learn from the part consistent with neuroscience and fill the gap with better design. For example, histogram or gradient utilize orientation features and a template for objects. The use of shape priors has demonstrated that the combination of top-down and bottom-up yield better segmentation results. Bag of features employ hierarchical representation of objects. The overall process of object identification is like building Legos. We assemble the parts first, then in the next stage, neighboring parts are grouped together to form the object. The first step is extracting basic features. Here, features are biologically meaningful properties. They correspond to processed information at the early stage of visual system, such as orientation, direction, edges, gradient, location. In the second stage, features are grouped locally to form simple shapes. Simple shapes are building block of object. They are similar to bag of words in machine vision. However, bag of words are mostly handcrafted, which is labor-intensive and require lots of customization. In our model, they are generated automatically following a set of biologically meaningful rules. This step corresponds to the intermediate stage of the visual system. Neurons have a highly localized receptive field and represent only local shape information. Lastly, neighboring simple shapes are grouped together to form object. This stage corresponds to late stage of visual system. Neurons at this stage contain global shape information. They respond to complex shapes such as hands and faces. Overall, the information flow from local points to edges, local curvatures, and finally global shapes. Match the hierarchical structure of the object pathways in visual cortex. In addition to the bottom-up process, both Stage 1 and Stage 2 receive feedback from higher levels. Feedback from higher level help improve the robustness and adaptability as they provide contextual information at a higher level. The top-down process helps modify the gain or saliency of features in stage 1 and help modify the grouping decisions in stage 2. Now, let's start with our demo. Our assumption is that object is identified through its shape. The reasons are humans rely on both shape and textures for object identification. However, shape cues is the first available. Shape help avoid the noise and fragmentation caused by clutter, occlusion, and changing textures. The first step is extracting features from the image, age, orientation, homogeneous regions. These features are almost sufficient to capture the property of a shape. In the future, better system could be developed by incorporating more features such as binocular disparity, depth, motion. This is consistent with neuroscience findings that there are neurons function as specific feature detectors in the early stage of visual pathways. In the top right figure, you can see edges with varying intensity corresponding to level of contrast between adjacent regions. In the bottom left figure, the image is segmented into homogeneous regions defined by their color, intensity, and texture. Each region is called a superpixel. It will help reduce interference of small edges for the next stage of processing. The bottom right figure shows the orientation of edge pixels. It's color-coded ranging from 0 to 180 degrees. Adjacent pixels with close orientation tend to group together to form lines or curvatures. Feature extracting step is mostly a bottom-up process, but can be also influenced by top-down process. The saliency of weak edge that consistent with object template could be enhanced. Additionally, feature filters need to be processed at multiple scales to ensure optimal signal. Similarly, in visual cortex, there are neurons with increasing receptive field in the visual cortex. Next, neighboring curvatures are grouped together and matched against templates to locate simple shapes in the image. This step involves both bottom-up and top-down process. The bottom-up process groups labeling contours to form simple shaped candidates. Adjacent contours or contours with opposite direction surrounding a common area tend to group together to form potential shapes. One thing worth noting is that the contours can span across multiple regions if they happen to be aligned along the same curvature. This is supported by the discovery that there are neurons responsive to single curvature or 2 to 3 consecutive curvatures, or neurons respond to simple shapes. There are neurons that integrate local contour features such as location, orientation, and curvature. It's quite possible that a curvature can be involved in multiple shapes as a result of this bottom-up process. That's why we need a top-down process to narrow down the selection to a few that are consistent with shape templates. In addition, contextual feedback from higher level help resolve the ambiguities of figure ground separation and help group dissimilar regions belonging to the same template or separate similar regions with missing or low contrast edges. This is supported by recent evidence that cortical feedback of global shape information from higher visual areas to lower visual areas may play an important role in the perception of shapes from contours.